Good morning, everyone. Good morning. Okay, good morning. My name is Wei-Song Shi, a faculty member from University of Delaware, and also the general co-chair for this year's IEEE MOST. Now, I assume everybody knows MOST is, right? I don't need to explain to you what the MOST stands for. So this year, well, first, we want to welcome you to University of Delaware campus. But I want to tell you that we all getting tired of using slides. You know, when you are a professor or you are a student at the university, you probably always expect a slides presentation. Today, I want to give you we will just talk. So what I found out very interesting is, if we don't use slides, people pay more attention, because once you starting have the slides, people can read the slides. They don't really listen to what we are talking about. So that's a very good excuse for our without the slides to welcome you. This is the third edition of the IEEE MOST. So I just give you, for those of you who is the first time, to give you an idea that back to 7 years ago, so when I was a faculty member at Wayne State in Detroit, so we're starting a local regional workshop called the Metro CAT. Represent for metro connected autonomous driving. And then after we running that for 4 years, we do see a momentum. There's a community starting look at this. There's a momentum. I remember Pedro, can you raise the hand? Yeah, even when we at the earlier stage, he's from Portugal, all the way fly to Detroit to attending this earlier workshop. So this gives us an idea that maybe at the same time, the landscape of autonomous driving, connected vehicles is getting bigger and bigger. So at that time, we started to talking to IEEE, make this become official IEEE conferences. So I think that was the idea. The first version was in Detroit, and then last year was in Dallas, UNT, and then this year we moved to University of Delaware here. So I want to, program-wise, I will leave it to the program chair, but I want to say a few words about this, the university and the campus. What happened is, for some of you who might be, if you are staying in the hotel Embassy Suites, Raymond, you might see on the way when you walk here, you see there's some construction going on. I don't know that. I don't predict that happen. If you see a little bit, I think it's still safe to work, but this is just showing another example of so vibrant of these campuses. University of Delaware is the 7th oldest university in the United States. For my international friends, maybe it's a good idea to know that 1743, even before the US was founded. And the state of Delaware is the first state of the United States. So that is where you are going. If you're looking for history, you should come to here. That's the history of the country is here. So when we Delaware moved here, the main campus is about 20 minutes. Well, technically, if you're walking along the South College, probably one traffic light, you will get into our main campus, which is a beautiful, typical East Coast kind of the buildings and etc. So I encourage you when you are here, spending some time, enjoy the food on our main street of the we call the main campus. We don't call the old campus. And then this campus, I want to say a few words here. Is about we call the STAR campus, stands for Science, Technology, Advanced Research. So this happens in 2009. When the Chrysler, how many of you know Chrysler? You still know Chrysler, right? Now they changed the name Fiat Chrysler. Now the Fiat is gone. It's now called Stellantis. So Chrysler, Dodge Durango. Sometimes when you're driving on the road, you might still see a Dodge Durango van. Durango's manufacturer is here. Is where you are sitting right now. Actually, this was the Dodge Durango manufacturer plant. And in 2009, when Chrysler bankrupted, our UD high-level nutrition purchased this land, 270 acres. That is, we make this since then became advanced. We call the STAR campus. So just now talking to Tom, one of the program co-chairs, Tom actually graduated from UD in 2014, not exactly, but 2014 as a PhD. Right now is at Meta. So every time when he come back, he can attest that the campus is changing. It's either has a new building is developing, or there is some other things. So this as you can see, the Wednesday afternoon, not Wednesday, sorry, Thursday is Tuesday afternoon. You will have William. Is William here? Yeah, William is our field demo chair. So you're gonna see some real demo our campus. Very proud, one of our students just developed a Waymo type of app. So you actually can on demand order one of our autonomous shuttle can take a ride from this building to our lab. Okay, don't go too far. We can't go to Philadelphia airport, but on campus you actually can we can run this right now. So that just give you an idea that this campus, I highly encourage you not just attending these talks, but also spending time talking to particularly our industry, participants seeking collaborations. That's the goal for these conferences. We try our best to invite, industry experts come here, like the keynote, tomorrow's keynote, and then the panelists you will see tomorrow. It's going to be, I hope it will help you build the collaboration, in addition to meet your colleagues here. I think that's what I want to, to welcome all of you to here. Enjoy the food. We are very proud of what kind of food options we have. For those of you who like Chinese food, a couple of weeks ago, there's just a Chinese Shanghai Xiaolong. Shanghai is called ugly dumplings, just opened. So that if you like that food, highly encourage you to go to give a try. Okay, with that, I will go to give it to my general co-chair, Xin Hui from Washington State University to say a few words to welcome you. Okay, Xin Hui.
Hello, everyone. I'm really excited to co-chair this conference. I attended last year in Texas, had really good impression. I'm excited to see the community is growing, and we see lots of young researchers in the field. I do think autonomous driving is changing the world that we're living in, and it will create a better future for people to commute and to do everyday life easier and better. And of course, there's a long way that we get there, but I think with all these young researchers, we see bright future ahead of us. And like Dr. Shi said, I'm from Washington State University, and it's really nice to explore the campus here on the East Coast. And it's exciting to know that there are lots of good food options as well. I hope for all of you, whether you were here in previous years or you're new to the conference, I hope you enjoy the conference. And if you have any questions or comments, please feel free to reach out to me or Dr. Shi or one of the program chairs. Thank you so much and welcome.
Yeah, I forgot to mention that I feel so bad for all of you. You have to come to a conference on Sunday. You probably never see this before, right? So the only reason is this nice facility right now is under the graduation season. I think business school just had this yesterday or the day before yesterday. Myself is also on campus yesterday for our College of Engineering ceremony. In order to get in 3 days, in consecutive 3 days, we have to starting at Monday, or we can do Monday, Tuesday, and Thursday. So that's not gonna work. So that's the only reason we have the starting on Sunday. Well, thank you so much for coming here, for spending your supposedly is a rest day, come here for the conference. So next, I want to invite Paul. Yeah, Paul Huang on the stage.
All right, thank you. Hello, everyone, and my name is Paul, and I believe all of you have received my emails, in some ways. So finally, We see each other. That's great. And I'm new actually to this community. I'm originally from robotics. That's my community. But it's great to see all the interesting and technologies that research happening in this community. And it's great to see all of you. And I just want to keep this short because we want to stick to the program. Just first of all, welcome and thank you for contributing to this conference. And without you, this won't happen. And the last thing is we have a 3 full packed program in next 3 days, including today, right? So hopefully all of you will join the program, will join the discussion, will join the food, will join whatever activities we have. Enjoy. Thank you. I will pass my co-chair to Tom.
Hi, I'm Tom. As Wei-Song mentioned, I graduated from here at UDEL about 11 years ago. It's my first year at most. Prior to Meta, I spent several years doing AI acceleration at both Tesla and Cruise. So it's good to kind of be back in this space. I think since we're starting to run a bit late, we'll move forward with introducing our keynote speaker. All right. So please welcome our next speaker, Vinay Palakkode. He's a distinguished leader in the autonomous driving industry. Vinay brings extensive experience from his tenure as a senior manager at Rivian, where he spearheaded the core perception systems modeling and deployment, as well as development of their driver attention system. His impressive background also includes significant contributions at Apple within their autonomous systems group and the technology development group behind the Vision Pro mixed reality headset. Beyond his work on autonomous vehicles, Vinay has demonstrated a broad range of technical expertise, from building inference accelerators for Apple SoCs to bootstrapping large-scale ML training systems. He is deeply passionate about tackling complex multimodal perception challenges across both robotics and mixed reality domains. Vinay is an alumnus of Carnegie Mellon University and a former member of the Illumination Imaging Lab within their robotics department, where he contributed to the development of the world's first AI-assisted automotive headlight system under Professor Srinivasa Narasimhan. Today, he will share his vision on perception's next frontier, world models, and the future of autonomous driving perception, offering a glimpse into the next generation of intelligent vehicles. So please join me in giving a warm welcome to Vinay.
Thanks, Tom. Just confirming you guys can hear me again. Cool. So really appreciate the kind introduction. Without further delay, let's just get started. Typically, most of my talks start with this funky looking image and very oversimplified story. So I would like to just start with the same one here as well. So I'd like to start with the very famous bit of AI lore. In 1966 at MIT, students were asked to link a camera to a computer system, and the task was to basically explain what exactly you're looking at. In hindsight, it almost looked cute, but we both can be like sure that this was not a summer project, and it definitely lasted several decades. So the reality is, many of you might have heard very different versions of this story, but the reality is also that this is a highly, highly simplified version of the story. Decades later, we are still working on solving hard machine vision problems. That's something we can agree upon. And perception is a profoundly hard problem for several reasons that we are going to talk about today. And I'll talk about the next big leap which we see on the horizon for autonomous driving perception as well. And one that might move us finally towards a solution that was wildly optimistic a few decades ago. While we do that, let's just do a quick reflection. So every so often, AI doesn't just inch forward, it just leaps. So consider AlphaGo in 2016, it beat Lee Sedol, the world's top Go player, in a 5-game match. Not too far after that, experts were super stunned because AI had achieved something downright superhuman, pulling off moves no one ever saw coming. Fast forward a few more years, we saw AlphaFold in 2020, solving the protein folding problem that stunned biologists for almost 50 years. It not only just folded the problems, but it solved it at an accuracy matching most of the expensive lab experiments would find. And let's not just forget the canonical ImageNet challenge, which started back in 2011, 2012. And by 2017, we kind of declared victory on top of that. And it's fascinating to see how many such step function changes we have witnessed over the years. But I keep asking, when is that moment of truth going to arrive for autonomous driving systems, especially in the perception space? Having spent 10 years in this space, one thing I am convinced of is that I cannot predict when that's going to be. But one thing for sure, we all could come together and then double down on understanding the why and focusing on the how to get there. Speaking of which, starting with the why, this might be super redundant for this forum, but I would still want to make sure we start with the why, just like I do in all problems. So why do we really build a superhuman driving agent? Straightforward facts to most, but I would still repeat that more than 90% of the traffic accidents are still caused by human error. And these are the NHTSA stats from 2023. And the numbers are just climbing. There doesn't seem to be near a spike. The second obvious win is unlocking the time and productivity. The average American is estimated to spend around 50 to 60 minutes commute every day. You can do the projections and kind of translate what that means for us. This is also a fair shot of enabling an accessible communication strategy and transportation strategy across all demographics. There are very few industries that can claim this. And on top of that, sustainability and environment benefits, which is a highly debated topic, but the aspects coming from improving traffic efficiency and a bunch of other aspects purely does add up. So that's another opportunity for us to solve. Now, all of this is hypothetical. What does that really mean in terms of finances and GDP impact? So I would like to basically flash your attention towards a study from 2023. This was basically a report funded by ARK Investment. Take it with a big grain of salt. It basically makes a bunch of assumptions. The key assumption to be called out is that if we can bring down the amortized cost of solving autonomous driving from, let's say, $1 million to a few $1,000s per unit, that's the unit economics. And let's just assume that we solve it in the next 5 to 10 years with a reliable fidelity. There is a projected gain of $26 trillion in the impact of GDP across direct and indirect revenue impacts. It's a mouthful to unpack, but the most important aspect is it is still a multi-trillion-dollar industry. So there are incentives across industry and academia to invest more in this. Having said that, let's just move towards the how aspect. Quick reminder, self-driving cars are essentially field robots. They do see world very different from humans, although we keep on comparing neural networks to human brains for multiple reasons. And most of the perception statistical analysis have been done by categorizing the tasks into very discretized operational domains. And then we basically look at the world in terms of static objects, dynamic objects, 3D lane estimations, and a bunch of other categorical labels. At least so far, so forth, that's how we have been operating. And that kind of also gave us a very straightforward modular architecture for the overall autonomy loop. So starting from sensing, then you have the perception, which is essentially what you see, what you perceive, and then you club with localization and mapping that feeds into the planning stack, and there is a closed loop controls and actuation. You can also have an optional loop from other sensor stack, but you get the idea. Now, what I would like to focus on is kind of a quick rundown of the history. We have always been in the world of late fusion for over decades. And what I mean by that is we just saw how a self-driving car sees the world around through a wide suite of sensors. Each sensors have its own unique characteristics. For example, LiDARs are really good at geometrical information to be propagated, but they're also sparse. And then there are different characteristics in terms of modeling reflectivity of the surfaces, et cetera, et cetera. When it comes to images, depending on the intrinsics and extrinsics, you are able to extract rich and dense amount of information, but it clearly lacks the capability to provide you the depth information as well. You can extend the arguments for all the sensors, ultrasonics, GNSS, each of them provide you a different modality. Now, the question is, how do you make sense by processing all of these together? And historically, we have been following what we call as a late fusion strategy. So For over a decade, late fusion reigned as a dominant paradigm in multimodal perception systems. And there were obviously good reasons for this, both technical and organizational. So technically, if you can think of each sensor modality, the ones that I've already listed, has distinct characteristics. So it was kind of canonically easy to assign engineering resources and research resources and build expertise on specific modalities because they all spoke kind of different sensing and processing algorithms. Software stack kind of evolved in isolation as well. That's just one motivation. The second motivation is also coming from the organizational structures. Say, for example, a lot of tier one suppliers were often responsible for specific sensors. So one vendor would build the camera stack, another one would build the LiDAR, and another would do the radar, and then they would provide a vendor-supplied solution, which was directly fused together in a much later stage in the autonomy stack. So it was a viable business model. It was a practical solution. It kind of sort of worked for quite a long period of time until it stopped working. And it essentially led to this siloed mode of development and a lost opportunity. And there are other reasons as well. For example, the whole functional the functional safety and system verifiability aspect as well. So in a late fusion design, individual sensor subsystems could be verified and validated independently. And this is very well aligned with paradigms like ISO 26262 or ASILs and similar standards. For example, if a LiDAR fails, the radar pipeline is intact. The modularity is testable. You can always have a fallback planning and you can isolate the faults, etc., etc. Now, but the safety-oriented modularity also came at a cost, which is lost synergy. So the late fusion models are literally blind to interactions between raw sensor streams, so they cannot learn nuanced correlations. Like a noisy camera feature might reinforce a very weak radar signal to disambiguate a pedestrian, and that's a lost opportunity, just to name some. So that's where the early fusion models began gaining traction, especially around, I would say, 2020. And with the rise of deep learning, we got to unify the languages spoken by all these different modalities. And there were a lot of other ecosystem development as well in terms of enhancements in training capabilities, scalable simulation solutions, et cetera, et cetera. Now, we could start co-training perception systems across modalities in a shared latent space. So early fusion typically allows models to learn joint representations, leading to better robustness, better generalization, and efficiency, especially for corner cases. So today, from all the leading OEMs, let's say Tesla's FSD, Waymo Driver, all the foundation perception models to several models of betting on early fusion, the shift reflects not just architectural innovation, but it's a rethinking of safety verification and modularity aspect as well. In fact, all the modern OEMs, which has some sort of monetizable level 2+ ADAS technology, leverages this particular solution. So moving forward, safety doesn't have to mean separation of components. It can also mean co-design redundancy, probabilistic fusion, and end-to-end verifiability. And we could build the tools to support it, which is exactly what the industry is doing right now. So let's just talk about the advent of early fusion. We did already talk about the diversity and characteristic differences across the sensors. And now the goal at that point of time was to basically find a unified space where we could resolve the view discrepancies. So all the sensor data needed to be efficiently transformed into this space with technically no loss of information, or at least with as much less loss of possibility of losing information at this point. And this space also needed to be suitable for different 3D perception tasks, such as 3D object detection, tracking, and map segmentation. Now, when you start thinking about early sensor fusion, you could think about scenarios where you directly fuse at the raw level signals itself. So typically 2 kinds of strategies kind of stand out. So the first one would be to directly think about how do we project the LiDAR to the camera plane and render the sparse depth and start making sense out of that. But as you can see, the difference in the nature of sparsity between these 2 signals are purely yielding geometrically lossy signals. If you flip this around, when we actually make this LiDAR-centric, we could technically colorize the LiDAR points with corresponding camera features, but then the whole point of relying on camera features was to get semantically dense information. Now that's kind of lost. So then that leads to the question, is there a middle ground? What do we do next? And that's essentially the start of the sensor fusion story that I want to tell. And the most important and the seminal work that I consider in this area is the web fusion. Please feel free to review the original paper for the detailed implementations and motivations. But I would simply start with a demo visualization. Essentially, what this states is you have a system that kind of uses raw sensor streams. In this case, it's purely cameras. It can actually directly regress 3D bounding boxes in the bird's eye view space. It can also do 2D to 3D map segmentation in the bird's eye view space. So all of this is possible, and you have one single neural network which goes from sensor stream to semantic task outputs, and this can be trained together in a multitasking manner. This has become more and more of a mainstream system, so might be quite familiar for most of you folks. But if you just think about how fascinating this was for the first time when I came across this. So this is the first time we figured out we could borrow all the computer vision ideas from a different variety of papers that we have read in the past. The information encoding strategies for different modalities come straight from different papers. If you look at the way how camera features are encoded, we have used a wide range of encoders ranging from ResNets all the way through to internal images kind of encoders. For the 3D sparse signals, like whether it's from imaging radars or LiDAR point clouds, we use strategies like point pillars or any other LiDAR encoding strategies which we have learned in the past. Then the only remaining piece was basically how do we fuse this in a geometrically consistent manner. And the strategy that was leveraged at this point in time was basically to use the intrinsics and extrinsics of the sensors. You do 3D raycasting. You essentially combine the geometric features in the perspective space with the features that you have learned in the 3D space from the other two, and you get a relatively dense representation of the 3D world. It still doesn't have any semantic meaning, but it's information rich that goes through an encoder-decoder structure. That's the baseline you work with. So now you can actually attach task-specific outputs, task-specific decoders. This paper, at least in this figure, you're just seeing only two. One is detecting static and 3D bounding boxes, which are basically objects around you. But you can also detect 3D lane estimates, road geometry. Possibilities are endless, and this is where it all started. Now, scientific community is very collaborative, very smart, so we keep on borrowing ideas from the neighboring domains as well. So one of the limitations was sensitivity towards calibration and the difficulty of fusion in the 3D geometry space using frustum raycasting. The clever technique that the subsequent papers tried to solve this was to basically borrow a page from the visual transformers. So now we have a spatiotemporal attention mechanism, which basically replaces that particular block. And what you get is essentially state of the art, which is being shipped in pretty much all the tier 1 and tier 2 systems today. And my team at Rivian built pretty much a variation of this team, and that's kind of powering all the ADAS core intelligence in our systems as well. Now, there are variations of this which introduces different sorts of supervision. The key factor to remember here is we have gone from late fusion to early fusion, but we still are in a highly supervised domain, which means we are always going to be data hungry, and this data need to be highly labeled. Whether it's manually labeled or auto labeled, you still have a really high dependency on building a high quality data set, which is an extremely expensive process. So what is the real problem at hand, right? So the first and foremost thing is exactly what I said. Because of the data hungry nature, it's extremely difficult to scale to different out of distribution scenarios. It's extremely difficult to scale across different operational domains as well. There is also a lost opportunity if you pay close attention. We do have a joint representation for the fundamental information where each of the tasks is derived from, but each of the individual tasks are still in silos. So earlier we solved the silos of developing information processing on a per sensor stream basis. That's gone, but our task level silos still exist. Third thing is these models are extremely good at doing exactly what we teach them to, which is to basically predict semantics. We show them bounding boxes, they detect bounding boxes. We show them maps, they will estimate maps. It fundamentally lacks the understanding of the inherent structure of the world, the geometry, the physics, everything that makes a human driver an intelligent driver. That aspect is completely missing. The other aspect, which is something which comes naturally to every human driver, is the aspect of memory. There are some variations of this implementation where you try to introduce a spatiotemporal queue, and then you kind of query into the past, and then that kind of simulates the notion of memory. But it's still far from what we would say is even remotely close to human intelligence for driving. And the most important thing, which is an extension of this, is counterfactual imagination. We are extremely good at kind of anticipating partially occluded scenarios or what if scenarios. You don't really have to experience what if scenarios like you exactly know if a 3-year-old kid jumps right in front of your vehicle at 30 miles per hour. You don't have to have been through the exact same scenario to make the right decision at this point in time. But that's not going to be true if we are in a completely supervised domain of execution, which makes this a completely reactive system and not a proactive system, nor is it predictive in nature. So we definitely do need something different. So the question is, what's that going to be? Now, this is also the time where we can also try to borrow a page from the neighboring domains. So what's currently missing here is a coherent agent-centric understanding of the world, something that doesn't describe what it is, but also can simulate what it could be. So the world models could build memory, understand cause and effect, and use imagination to plan. So they fuse inputs not just in an early manner, but also in a useful manner. And you would start seeing emergent properties out of that. And this shift from task-specific unsupervised perception to holistic world modeling isn't just a technical upgrade. It's a fundamental paradigm shift. Tooling needs to evolve, thought processes need to evolve, validation methodologies need to evolve. So what we have is still a lot of nascent systems. There's a far road ahead of us. What my goal is to at least give you a preview of 3 or 4 such proprietary technologies and see how we can advance or accelerate the development in that direction. Now, just like we did in the previous 2 approaches that I mentioned, one clever strategy would be to kind of borrow ideas from the progress in our neighboring domains. So over the last 5 years, the whole GenAI wave has shown us what's possible when we train at scale with the right objectives. So if you look at GPT and similar LLMs trained using next token prediction, they reveal that prediction is more than just a loss function. It's a way to internalize the structure of the world. So when that idea extended into vision and multimodality, like in Flamingo, Gemini, Claude, these models didn't just describe what they saw. At least they seem to have understood. The word is seem because there are still 2 schools of thought. If you're on the Ilias team, you would say this is still like perfectly reasonable. But if you're on Jan LeCun's team, you would say this is still a statistical model predicting causationless correlation. So moving further along, we saw variations with diffusion models like Sora, which attempts to push this further, not the word attempts. They simulate rich feature scenes, not as raw pixels, but as structured trajectories. So these are exactly the kind of capabilities we want in autonomous agents: memory, simulation, reasoning, and planning. And not by stitching together task-specific modules, but by learning an internal world representation. So we have a latent representation we already do in even the current BEV systems, but we need a latent representation where imagination, perception, and decision-making kind of emerge organically. So instead of seeing the world as some exotic departure from the current models, I would say we should see this as a direct evolution of everything GenAI has already taught us. It's time we bring these lessons from pixels and prompts into planning and perception. That's the way I kind of look at it. Now, we use the word a few times, so I just wanted to just formalize this a little bit. So one thing for sure, in order to drive safely, we got to be able to predict the future. We do that with holistic understanding of the world. And that starts by not looking at the world as a set of discrete categorical labels, which we process to make decisions. So a world model is typically a generative model that predicts what happens next, conditioned on some context. So the context can be past behaviors, it can be past observations, can be as simple as a language prompt or even a counterfactual description, which again can be a variation of the prompt. Let's just say if we go in that direction, and then if we have modernized the stack, what would that look like? All of a sudden you have a defragmented tech stack. And once we solve for it, the maintainability as a living, breathing piece of software will get significantly easier. We could also think about conversational capabilities and chain of thought reasoning as something that could serve as a partial, if not comprehensive, means of interpretability, which is going to be a huge feat and a missing tool as it stands today. Now, the real thing is these are very, very nascent ideas, very, very nascent ideas in the sense that half of them are proprietary, which means we have to go off of the demos and you have to kind of trust what's out there. Some of them do have published information with partial data, so there is not enough reproducibility, but you would still see tech papers. You can kind of guess the strategies and underlying mechanisms here. So I would like to provide a brief overview of 3 recent really interesting take on this problem. And please do realize the intent here is not to provide a comprehensive analysis of the work done by any of these amazing industry friends and folks in our community, and also includes academic researchers. But rather, I would paint in broad strokes the promising direction it's heading towards. And most of this, if not all, are far from ready to be deployed on the edge, which is something we can talk about. And honestly, this is not the first time we have had this problem. Like, think about like how much the inference and training acceleration infrastructure has come over the past 5 to 10 years. So the first approach, I would like to start with the approach our friends at Waymo had taken. So let's zip through the capabilities, inputs, outputs, performance, and limitation. So the fundamental idea here is that there is a camp of researchers who strongly believe that the text, especially the text in the internet, is a projection of world knowledge. Again, the vote is split on that, but let's just go with this. So developed by Waymo, it utilizes a foundation of multimodal large language models to process diverse inputs and generate comprehensive driving outputs, aiming to unify tasks like perception, planning, and mapping. And it's essentially built on top of Gemini, LLM. So you have a lot of foundational knowledge from the internet already modeled into it. The question is how much of zero-shot transferability can we actually get out of that? And it's also trained on multiple tasks at once, and it definitely fuses raw sensor data with language-style prompts and returns all critical driving outputs in one pass. So if you can look at it, it's consuming surround view camera streams and past ego state. And because it's Waymo, they do have millions of miles of real data in terms of mileage accumulated and also virtual miles accumulated in simulation, along with operator and driver logs, which acts as soft prompting and metadata for this information. And that kind of is the baseline, and essentially that's the fuel that kind of drives this innovation here. Now, given a textual task prompt, it returns driving critical outputs like any of these semantic task output that you're looking at right now. Now, the beauty is, just like we would want to move away from a complete supervised learning paradigm, now we are looking at a completely self-supervised paradigm here. So the only supervision it kind of needs is the future location of the EJO vehicle. So no dedicated human labels, which is a huge win, and it's completely HD maps free. So just to give a very specific example, so if you're dealing with the task of trajectory estimation, trajectory prediction into a short planning horizon, you represent your trajectory as a list of waypoints, and then you basically feed your Gemini-based models with your targeted intent, your ego state, and the video features. And the self-supervised learning strategy kind of adapts the next word prediction, exact same strategy up to a certain extent, and then it kind of transfers to this particular domain. Now, this is formulated as a generalist in this driving domain, but it also is kind of trying to solve around 10 autonomous driving tasks grouped into 3 categories, starting with spatial reasoning, road graph estimation, and scene understanding, which pretty much covers a broad spectrum of otherwise 3D tasks we were dealing with the performer error. Now, what's more interesting for us is this system deals with inputs and outputs purely in the form of textual encoding. So it just gives us a hint into the future, which says that if you can prompt the model in the form of driving instructions, it can respond in the form of driving behaviors, right? So that's something foundational. There is a very high confidence bet that you can say that the internal representation this model has learned has a lot more density and entropy compared to the models which did not have the understanding of the world otherwise. There is some amount of training details available, but I would really be surprised if you'll be able to reproduce any of these results, because around 4 million scenes are from women who put a test set, but they also do claim that they used a lot of internal data sets. So I'm not positive about reproducibility, but the key ideas are already out there. Now, how do we convince ourselves that this is an acceptable research direction? So if you go off of 3 or 4 counterfactual examples they have given. So the first example, you can actually see in the ego path, you see a garbage bag, and then there is an anticipated trajectory course correction where you kind of swivel around that. The reality is that the dataset never had this particular scenario, nor did it have explicit labels for any of these object taxonomies. So it is clearly going beyond the static vocabulary that it would have learned otherwise in a supervised setting. So we are kind of breaking the open vocabulary barrier at this point in time. There is another example which does something similar for objects. In a typical supervised learning world, you would start off this as categorizing objects into a certain category. At some point, there will be a taxonomy explosion. Then you kind of club all the unknown objects into one different class. That becomes the hardest class to solve for, and then it kind of becomes an intractable problem. So that gets greatly simplified. So I would say +1, that makes sense. Now, if you just look at the next example, you would see something similar as well, where you would see a dynamic object, which is a living being here, which is a squirrel, which kind of jumps into the ego path. It kind of does predict a very similar swiveling pattern in its driving behavior as well. This is again an unlabeled scenario. There isn't any sort of categorical label for squirrel, nor does it have a motion model for squirrel, the way how it's going to behave. So the model seems to have learned it implicitly from the world knowledge it has acquired from the other modalities, and it is aligned during the training process. The same kind of examples you can kind of extrapolate into other tasks, whether it's like 3D detection, row geometry estimation. So all in all, I feel it's a promising direction. The results may be handpicked, but it's still worth pursuing further. Having said that, if you just take a closer look, it does come with a huge number of limitations than the benefits. In fact, probably like an order of magnitude more limitations, just as any other technology in its nascency. So first thing is, the current system results that I could review, they only had a history of 4 frames. So in a 30Hz system or a 60Hz system, that's not even 100 milliseconds planning horizon. So it's not a practical system, but it definitely gives us something to get started with. Now, this is a purely text and other modality, plus the only sensor stream or the dense sensor stream it's working with is cameras. So the inherent notion of depth kind of disappears, and then integrating LiDAR models with that is going to be even more expensive, which leads to the last point, which is the challenges of onboard deployment. There isn't any statistics on the inference latency or training complexities, but they've already mentioned that this is based out of Gemini. So you're looking at hundreds of billions of parameters. So this is not something deployable on edge anytime soon. The other 2 aspects are verification of the predicted driving signals, which means all of the evaluations, whether it's quantitative or qualitative, it's been in an open loop scenario. So you don't have a closed loop scenario where we can actually quantify whether the generated motion plans are actually verifiable, which is the second last point. So the sensor simulation with long loop fidelity, where you kind of render the actual scenarios along with the sensor data, is going to add even more cost on top of that. So the challenge at hand is purely infrastructural to begin with. How do we make sure that we have a strategy to kind of trim down the weight spaces, inference latencies, end-to-end training latencies? So it's an AI infrastructure play to begin with. So we saw a scenario where there is early sign that we could model the world knowledge purely in the form of conversational text forms, which can be decoded into very specific tasks. In this case, say, for example, you could see that the output is still task, but task in the text form, you could decode them into visualizations and video or any other forms. You just move to the next section where you are a bit more closer to the actual modality and operational domain. So this is the work done by the team at Bobby. It's called Copilot 4D. So essentially, this is one step forward in terms of what goes into the model and what goes out of the model. So this is an unsupervised world network. Here, the world knowledge is used to forecast the world itself. So the model is capable of probabilistically forecasting a distribution of what comes next. In layman's term, you essentially predict what are you going to see next in terms of the input itself. So let's say if the inputs in this case are purely LiDAR signals, you're kind of forecasting what the next n frames into the future of the LiDARs will look like. So models like GPT have achieved remarkable scalability by predicting the next token. So the same idea as in the previous one. But there are two big challenges which are highlighted in this effort, and they've kind of done a reasonably good job in kind of solving that. First one is, unlike text data, the sensor data from physical world is high dimensional and unstructured. So when you tokenize them, they're kind of intractable. So you need to bring it into a tractable space to begin with. Second thing is the scalability of autoregressive models in general. So all the GPT style models, traditionally they regress one token at a time. I would say traditionally and typically there are optimizations like speculative decoding or other techniques which you can do. So that assumption doesn't hold here. But if you try to kind of simultaneously decode multiple tokens, you kind of implicitly make an assumption that these are mutually exclusive and unconditional, which is also a wrong assumption to make. So how did they go about it? So the first trick was essentially to make the input space tractable. So you basically use an old trick. You basically use the variation of visual Q&A technique and VAEs. So all of a sudden you have input space which is discretized and tractable. The second thing that they could do was essentially make an alternative formulation. So you basically derive few principles from diffusion models and you make it in the discrete domain. Cleverly figure out how you can actually scale the inference time compute as well for this particular scenario. So what does this give? So it basically gives us a three-staged framework. Unlike in the previous case with Waymo, you're dealing directly with the sensors you would get from the vehicle and you're trying to predict the same thing. So first stage, you would essentially tokenize your LiDAR signals. Second stage is your actual world model. So you basically learn the exact space, bird's eye view representation we saw in the previous papers, but all of a sudden now it's in 4D because you're looking at time as an additional axis. Now you have a third stage, which basically predicts the next tokens, and then you kind of use a differentiable rendering technique to produce a realistic looking point clouds. And that is exactly the future that you're trying to predict. And because it's a probability distribution, if you're looking at like n seconds of future, you're looking at multiple of them at varying level of uncertainties, which is a dream if you're in the world of planning domain because you have different levels of confidence and you can pick and choose and have your smartest planning algorithms or heuristic based, so you can have a learn planner on top of that. Now, what does this mean for us? So it directly models raw sensor data in an unsupervised manner. That's great. However, apart from the quantitative metrics, which are also very narrow in this paper, they've also shown when we have a scenario such as, think of any counterfactual scenario, like if you're driving at highway at 75 miles per hour, for some reason, suddenly you've had to decelerate and then brake. There are visuals in their proprietary videos which shows that there is evidence of model being able to predict that some of the vehicles behind the go were also able to brake them and mimic this behavior. And this kind of hints that the model anticipates some of the possibilities that it would not have been able to do without the understanding of the world. So that's another positive sign. And there are a few more other examples which kind of gives us more confidence that the decision making is actually happening based on its intrinsic understanding of the world and not just the taxonomy and the labels it has seen in the training time, which is definitely a fascinating direction for me. Now, what are the other limitations? We did mention about evaluation strategies and quantitative metrics not being strong enough. The other two or three things worth calling out is the most important one is this is a LiDAR only or LiDAR as a principal methodology. In reality, like most of the commercial systems, in fact, very less likely to rely on LiDARs unless it's a ground truthing system, Waymo being an exception. The other aspect is you do lose a lot of semantic richness because you're not dealing with cameras at this point in time. And then there are some quantization noises that can also affect the fidelity of the signals. TLDR, there are more issues than the benefits, but again, it's going back to the same bucket. It's just giving us early signs that we could rely on unsupervised learning to build much better understanding of the world, which has not been the case like a few years ago. Now, the last one, which is probably more interesting, is the action-free forecasting. So right now, the prediction of future is it's somewhat unconditional. So you have previous observations and you basically get the next observation. But if you really want to test your hypothesis, whether you really understand what the world you've modeled, you got to be able to condition it. And what I mean by that is you should be able to ask what if questions like, what if I encounter the same scenario, but the time of the day is different and the weather is bad, where it's raining at some level of rain density. So if you can ask these questions and prompt the model in any of the possible ways, it doesn't have to be textual, but let's just start with text. Then you're now talking about a verifiable way of understanding the model's knowledge. And this particular approach clearly does not support that. So that's definitely the most critical shortcoming in my observation. That leads me to the third approach that I wanted to talk about. Unfortunately, this is the most proprietary one, which means I have very little math and practically no videos to show. So I'm sure most of you are familiar with this company called as Wave. The idea is, how do we extend generative AI for the entire autonomy stack in a controllable manner? So if you can go back to the website of this particular company, you would see that you have controllable knobs for a wide range of scenarios. So you could start with time of the day, weather, driving patterns, edge case scenarios, right? It's like a wide range of scenarios that you will never be able to collect statistically significant amount of data. So this approach, purely aiming at controllable sensor data generation, predominantly multi-camera, that's another highlight. And then you get multi-view consistency as well. So if you're almost able to dream your multi-sensor configuration, which is information rich. But I guess what is this based on? So past videos, and the foundation model also consumes exactly pretty much all the information you saw in the Waymo's approach. So you can take all the text form data, you can take the IMU data, hundreds of thousands of miles worth of data, but it's still in the unsupervised manner. And this is extremely beneficial for the auto distribution sample generation for long tail scenarios and corner cases. Now, in terms of underlying architecture, what we could probably learn more about, it kind of is a blend between spatiotemporal transformers and discrete domain diffusion models. But the key idea remains the same. So this is not too different from any of the controllable video synthesis, like if you're familiar with OpenAI Sora or any of those approaches. You basically learn a latent representation, which is another word for the world model that we've been talking about. And then the prompting actually happens right now in the discrete latent space itself. So the prompt that you actually type in the form of text form basically gets directly injected into the latent space, and then it modifies the behavior. So this is probably the most practical and scalable way of producing a real world simulator for corner case generation, which probably is the most realistic and practical way of testing our hypothesis, like how well have we understood or how well have we modeled the world. These three approaches gives us three promising directions. But if you haven't observed this, let me just call out all three are heavily funded by industry. So they are practically proprietary technologies, maybe except for the Copilot 4D, where there is at least a fully published reproducible results. Now, that is the key problem in my opinion, because we got to join forces in this particular venture. Now, as a closing remark, I definitely do want to basically call out the key areas which I think we should come together as a community, because I think this is a really promising direction. We really need to advance this. The sooner the better. And it doesn't need to be like one single effort that touches all aspects of the tech stack, right? Like if you look at the inefficiencies that you can solve purely at the AI infrastructure layer, there's a whole lot of things that you can do, like test time compute scaling, tighter collaboration with hardware accelerators, designing purpose-built hardware accelerators for inference acceleration. There's a huge range of research avenue which is already in flight. All we need to do is characterize these models and have more tailor-made solutions for that. Apologies. Second thing is we still do have some of the same problems that we have in the supervised domain here as well. First and foremost being lack of generalization. This purely comes from the fact that we do not have a closed loop environment to validate these systems. So we can prompt them, we can visually verify them, but unless you have a high fidelity closed loop simulator where you can have rule-based systems to evaluate these, we are kind of back to the human in the loop system. So you will have to trust the technology, but you won't be able to verify that. And that kind of comes, the next point is kind of an addendum or corollary to that, where you need to be able to like bridge that gap between sim and real. Last thing is, it's kind of interesting because interpretability was one of the motivations for going in this direction, but it still remains largely unsolved whether breaking down the responses through chain of prompt reasoning is an authentic way of validating what the model is actually learning, right? So there are 4 different streams of investigations which are already in flight, and this is already happening across the Gen AI landscape. It's not unique for autonomous driving industry. But if all these 4 are kind of lined up in n number of years, then I think the future is more bright. I'm definitely optimist, but all of this in a nutshell, it just screams for one word: standardization. So I hope like each of the proponents and like us having like a vested interest in solving autonomy, I would say let's figure out what are the strategies in which we can collaborate and push the needle on this front. With that, I'd like to wrap up this talk, but I'm happy to answer any questions you may have.
All right, thanks, Vinay. So do we have any questions for the speaker?
Thank you, Vinay. This is the best, the keynote, what we are really looking for. So in addition to all these ideas, you also threw these limitations. I'm sure that many of the students will find that this is very useful. Okay. I do have one question to you, though. So if you're looking forward, for example, you mentioned that sometimes that, you deploy a model on the vehicle. Now later on, you might try getting a revised or updated models. So basically, how you gonna, I want to hear from you, particularly from the industry point of view, that the model update on the existing vehicles, what's your view on this?
There's a lot to unpack. So is your question specifically in the context of deploying world models and continuous improvement of that? Or is this a question about how do you typically strategize about model updates independent of what kind
Well, actually, I'm glad the question is, for example, at the beginning, when you ship this vehicle out, you might deploy the randomly pick example, Emma. And then later on, through the research, your company decided that, oh, I want to change into the other models, like And in this case, what is the current state of the art from the industry? How do you going to update these models on the vehicle?
Yeah. So I think I understood the question. So I think the simplest answer for that is the entire paradigm of world models is at its nascency. So none of these are actually close to deployment. Now, when we get to deployment, one thing that we can be sure of is that none of these models will be deployed in its current form, because world model, as the title suggests, it's just the internal representation. What we will be shipping they're going to be the more task-specific outputs, right? So you might still have a model which basically produces control signals or verifiable motion plans directly that comes out of that. So what I envision is that you would have abstractions like, for example, I can give you very specific examples. If you're familiar with middleware abstractions provided by companies like Qualcomm or NVIDIA, you would have, just like you have abstractions at the middleware layer, you will have an abstraction at the model deployment layer as well. And that would look something like you define your input as a hardware abstraction layer. You define what is the compute requirement. You basically kind of define that as a deterministic computation graph with some sort of statistical guarantees. And then you will have tasks, and the interface or the output of that task will have exact parity with current day's driver system. So it should be like a plug and play system. You should be able to like completely replace the existing modular architecture with this particular architecture, because inputs are the same, outputs are the same. What changes are what goes in between. Now, to get to that point, we have to like cross a lot of hurdles. Like one thing is, how do we get it down from hundreds of billions of parameters to like something that's in the order of 100 megabytes or 200 megabytes? What sort of inference optimization strategies do we need? Can we borrow things directly from LLM world, or can we bring some of the old school computer vision techniques here? There's like a wide range of open research topics, and I hope at least some of you get inspired about picking up problem statements in that direction, because this is probably a multi-year, potentially a decade worth of work to be done there. Does that answer your question, Professor? Yeah.
Hi, Vinay. It's really a very excellent talk. And I just have a question regarding the speed, because you mentioned lots of future directions, like different control policies. But like actually when the speed sometimes tell us like the context. When the speed is very high, is usually we drive on the highway or rural area. But when the speed is low, like we usually drive in the cities. So like, what's your point of view or industry's view regarding the speed influence to the different policies? Or is there any future directions you can think about, like combine the different like control policies, but also include the speed influence?
I think that's a fantastic question, and that is a very foundational premise of the talk itself, right? Like so world models are not just about the solution that you deploy, but it also provides you a framework to arrive at that solution. And your question is, how do we design the optimal control policy depending on all the scenarios that you said, right? And then approaches like the third approach that I mentioned that Wave is taking is a canonical example where you can define a distribution of possibilities, you can simulate them, and then you can identify what's the right policy. That's one. Second thing is, because this is a safety critical system, and we have moved away from verifiable safety strategies like ASLDs, you have to have statistical guarantees. So you almost always have to plan for the worst case scenarios to make sure you save lives. And what that would mean is, I think I touched upon this when we were talking about Emma. The current system, even if you run this on a server side with the current memory architecture, you're not able to deal with more than a history of 4 frames. In reality is just working through that number, right? Like if you want a 1G deceleration profile at 75 miles per hour on any of the highways, you're probably looking at accumulating potentially like 20 frames worth of data, right? If not more. And that information has to be multiplied by all the modalities. So if you have a multi-sensor system, you're looking at probably 20 frames times 6 camera frames times 4 LiDAR frames plus few ultrasonics and radar sensors. So you got to architect a system which can actually process this data within that, ultra low latency budgets of like less than 800 milliseconds or so. So it's a combination of how do you provision your hardware, how do you understand your limits, and how do you verify this using the world models itself, and then you deploy one of these world models. So if you think about it, it's like kind of fascinating, right? It's exactly how we are working. Like we are trying to understand what our brain is capable of, but in fact, the brain itself is trying to ask us the same question, right? So it's my brain trying to ask me, what is the brain doing? We're kind of trying to do something similar with world model. We want to learn about the world, but let's use the world model to kind of verify what world models will look like in the world, which is one more reason why I'm always fascinated about this particular avenue. Does that answer your question?
Do we have any more questions?
Thanks, Vinay, first of all, for this very good talk. It was very helpful. My question for you is more on the inference side of things, with the shift towards more world models and vision transformers. How do you see the landscape of model optimization changing, and are there any emerging trends that you kind of recognize there? Yeah,
so I think the good thing is I think this is where the power of open source and power of scientific community kind of keeps coming back, right? Like they keep borrowing ideas. So I don't know if maybe you're familiar with the work, right? Like, so 5 years, 10 years ago, we were mostly dealing with GPU based acceleration. Then over the years, now we have seen purpose built SoCs and hardware accelerators for different workloads. Initially, it was just for computer vision workloads, and then for classical ML workloads, and then just accelerating coordinates. Then over the years, we saw the advent of transformers, which kind of threw all the assumptions out, right? Like all of a sudden, the goal is no longer just to have more math to be done per unit of data that you move. Now we also have to move a lot of data because these are like data flow heavy graphs. So that's when you saw advent of companies like Cerebras or Sambanova or even Grok. So I think the landscape is going to evolve, but the good thing is that there are only few foundational pieces, especially in the post-transformer era and the advent of Gen AI era. If you have figured out various configurations of implementing spatiotemporal transformers, I think that kind of gives you a segue for traveling long distances. Within that, you can spin off in the vertical stack, right? Like you can start all the way from fusing operations at the graph level, at the highest level of abstraction, all the way to abstracting the last level of DMA transactions in the ASIC that you're dealing with. If you're somewhere in between, you can think about precisions, FP8s, you can think about aspects like quantization-aware training. So all the things that you have done in the pre-transformer world also comes in. Now, when you combine that with other clever strategies like, reformulating transformers from transformers to like using mixture of experts, which is like a slightly different formulation, but which kind of yields similar results, or moving from I don't know, like for image encoders, like I mentioned about the input embedding extraction, right? Like in many cases, just playing with the precision alone kind of gives you a long segue. But the biggest gap for me is not actually compute. We got to figure out how to solve the data flow problem, because the order of magnitude of data that we need to move has exponentially grown up over the past few years compared to the actual compute requirement, because compute has become cheaper and cheaper, but memory and data movement have not been. So what I don't have, or maybe like this is Tom's area of expertise, he may be able to add more value here. But the thing that I'm really looking forward to is see like which is that one single solution which kind of tops all the benchmarks that we see today, and that kind of future proofs how quickly we can scale transformers with a very attractive unit economics. So I don't want to look at benchmarks like we have a training side server with fastest number of tops in decoding Llama 4, but I also want to see that in a reasonable amount of time and cost, and that's the real name of the game at this point. I know it's a bindy answer, but hopefully that kind of gives you what I'm thinking through.
Thank you.
Hi, thank you very much for an excellent talk. Chaudhry here from University of Buffalo. So I think for all the three approaches you mentioned, this all seems to have one limitation where to close a loop, to have closed loop evaluation, it takes a lot of effort or simulation effort to do that. I wonder, as a world model, it has this feedback structure naturally. So what do you think it takes to actually acquire this closed loop capability, whether it's just computation advance or actually something fundamental in the model side to reduce the model such that it can do this closed loop evaluation? So wonder your opinion on that.
Fantastic question. I'm really glad that you asked this. So I've been thinking about this. So I think the feedback, purely because it's unsupervised, is coming from the trust that you have in the source of the data, right? So if your driving logs consist of good driving behaviors, and then you have come across different permutations of cases in the latent space, you might be able to prompt and combine and synthesize novel scenarios. But that may not necessarily be true. Like for example, some of the obvious traffic rule violation scenarios, which might be easy to script in behavioral agent-based simulations or behavioral long loop simulations, which exist in the autonomous driving industry for quite some time, right? You can write finite state machines, or you have ways of modeling rule breaking systems. How do you produce that kind of feedback, right? Like unless you explicitly somehow introduce variations of that in your real world driving scenario, which is a reasonable assumption to make, but I wouldn't bet a safety critical system success purely based on that level of feedback mechanism. Now that's my current thought. As and when I get more information and more background, I'm happy to revise the framing around this problem. But it's a very interesting question, and I think we should all like keep thinking about that, because that's one less thing to worry about. If you figure out how you can implicitly introduce that feedback loop, then it's a substantial investment that you can, reallocate that resources to something else, whether it's the infrastructure cost or actual computational cost. It's better spent elsewhere. Fantastic question. Thank you.
Thank you for the great talk. I think it's a great summary for some of the recent exciting research work in world models. We have seen things such as Gaia 2 and also the NVIDIA Cosmos model as a pre-training backbones. So I'm more interested in learning about your aspects, bringing research into production. Particularly, I'm interested Rivian as a great example for vertical integration. What is your strategy at Rivian in building end-to-end autonomous driving stack? Can you share what's the strategy in adapting this, moving away from a modular implementation to a more end-to-end trajectory prediction using world models?
Yeah, so unfortunately, I won't be able to comment about unreleased products or features. Some of the strategy will directly tie into that. But what I can tell you is, I think you nailed it when you mentioned about the vertical integration strategy, because that's been really helpful in slightly different ways. So vertical integration typically means owning the sensors, low-level software stack, all the way till the ASICs. But because Rivian owns the vehicle platform as well, so there has been consolidation across ECUs as well. So that was one of the reasons why my team started working on this early fusion approach and migrating all of the legacy late fusion approaches, because each of them were processing in their own ECU. So that sort of vertical integration brought the system together. And the basic strategy is not too different from what Andre Karpathy and team did at Tesla. So we systematically start eating into the stack. So basically you start folding in late fusion into early fusion. So now we have already shipped an early fusion system. Now you combine early fusion detection with tracking, which is almost a done deal. Like internal customers have already started getting that. Next step is folding in behavior prediction. And that's where I can talk about. Holding in planning and controls may or may not be in the plan, but I can't comment about that. But the strategy is something along the same lines, and that's a time-tested strategy, because Tesla has been doing that for like close to 7 years, and they were also statistically safely deploying it for the same systems even after removing some of the sensors, right? Like LiDARs were removed, vendor-supplied Mobileye-based solutions were removed, and some of the radar sensors and ultrasonics and were like incrementally removed. That's a high confidence strategy that I feel pretty much any OEM should be adopting. But the jump to world model is probably something I would be very, very cautious at this point. Hope that answered the question.
All right, thanks. That's all the time that we have for questions. So Vinay, since you're not here with us, we have this plaque to share with you. Once you get back to the States, I can give it to you directly.
Oh, fantastic. I'll catch you up in the Bay Area. Thanks a lot. Thanks, folks.